So one of the first things I'm going to review is we're going to talk about collision theory of reactions. So how do reactions actually take place? Okay, and we've already kind of discussed this earlier, but essentially for a reaction to take place, to go from reactants to products, I have to break bonds to form new ones. Okay, that's the only way I can rearrange these atoms. And we're still following the law of conservation of mass. We can't create or destroy matter. We can only rearrange the atoms. And the reason why we can rearrange them is, well, if they're sharing electrons, which are bonds, we could break those bonds and form new ones to make them stable. So we see here clearly, we have a reaction of nitrogen, which is an element, it's a gas, it's a diatomic, Brinkelhoff. And we have oxygen, it's also a gas, it's a diatomic. And these two elements can combine to produce a compound. Now this is a covalent compound because it's two nonmetals, it's binary covalent, and that would be an example of nitrogen monoxide. Okay, so but for that to happen, we actually have to have a collision. The reactants actually have to collide. And not only do they have to collide, there's a couple of key elements for this collision, okay? What I always tell people, for a collision to form products, it has to be referred to as an effective collision. And what I mean by effective is when they collide, they actually break a bond, okay? Because sometimes these collisions, they'll just bounce off each other. We saw that when we were talking about kinetic molecular theory in the gas law chapter, where some of the collisions will just result in them bouncing right off each other. So to have an effective collision is different. You could have collisions that don't result in bonds breaking. So what do I mean by that? To have an effective collision, I have to have enough energy to break the bond. If there's not enough energy, the bonds won't break and the reactants will just bounce off each other. Another key, and this is really important, to have an effective collision is you have to be in the right orientation. So what do I mean? You have to be in the right angle to break those bonds. So you can collide, these reactants can collide with enough energy, but if they're not in the right orientation, the bonds won't break. So an example, if an O2 molecule collides like this with nitrogen, it may not result in the bonds breaking and producing two nitrogen monoxides. So the two keys are I have to have enough kinetic energy and I have to have the right orientation or the right angle to break the bonds. And those are the two criteria of an effective collision. So we talked about this. And to meet that effective collision, so basically, we're talking about effective collisions. To meet that effective collision, that essentially is referred to as the activation energy. If you've taken biology, you may have heard of the concept, the transition state, or you may have heard of the concept of the activated complex. Basically, the activation energy is the minimum amount of energy for a reaction to take place with the proper collisions, okay? And those proper collisions, again, I refer to them as effective collisions. So in this particular reaction, you have to go from your reactants to products, and we've studied that this difference in energy right here is what we were calling heat of reactions, okay? And here we see that the reactants have a lower potential energy than the products, so this would be an endothermic reaction. This is an endothermic reaction. Why? The products are at a higher energy state than the reactants. But what's even higher than the product's energy state is the activation energy. So you have to meet that activation energy for this to occur. Now, If you're thinking that it only goes in one direction, right, you would have to travel up this way. But what we have to start looking at, if I have a closed system and now the products are allowed to react, I could go back up in this direction and produce the reactants. That's referred to as a reverse reaction. So the reaction rate is the speed at which a reactant is used up, okay? And reaction rates are going to be influenced by temperature. So the reaction rate is the speed at which products form. So basically, the reaction rate is how quickly reactants are used up and transformed into products. Increases in temperature typically causes molecules to have more kinetic energy. We learned that in kinetic molecular theory, and they're moving faster. If they're moving faster, the frequency of collisions goes up and their energy as well goes up. But most importantly, the frequency of effective collisions increases. And again, effective collisions means collisions with enough energy and the right angle to break bonds and form new ones. So by increasing temperature, things are moving faster. There's a higher frequency and probability of having an effective collision, and we refer that to as activation energy. So what would be the effect of increasing the concentration of my reactants? Okay. So if you increase the reactants, you're increasing the number of collisions. If you increase the number of collisions, you're going to increase the probability of having an effective collision. And if you increase the probability of having an effective collision, you're going to increase the reaction rate. So the diagram over here on the right is showing, okay, let's say I increase one of the reactants, right? If it's a 1-to-1 ratio, we got one possible collision. If it's a 2-to-1, now I have two possibilities. If there's 2-to-2, now I have four possible combinations. So what we're seeing is as we increase the concentrations of the reactants, increasing the probability of an effective collision. It's all based on probabilities. So I went through that a little fast. So going back, we've talked about two things. How temperature affects reaction rate. It basically increases it if you heat things up because you're moving faster and there's more effective collisions. If I increase concentration, reaction rate increases as well. Why? Because the probability of a possible collision occurs.
I had a comment on that.
Sure.
Is it is this like relatable to like saying like you're boiling water and putting soda, like salt in there, so when you heat up the water it breaks the bonds?
Not oh, you mean with dissolving the salt?
Yeah, dissolving salt, is that like kind of relatable?
Yeah, it's very relatable with the dissolving. I thought you were referring to boiling point elevation, but
Oh no.
yes. So that goes back to solubility rules. And if you look at the videos with the solubility of different salts, we saw that all the solubilities increase, right? The number of grams of a salt per 100 grams of water, those solubility limits increase with increase in temperature. And it's exactly for what you said. The water is moving faster. And when the water is moving faster, it can basically go into the lattice structure of the salt, dislodge those ions and surround them in that process that I called solvation. Solvation is where the water can surround an ion. But if you're heating it up, now the water is moving faster. It's colliding with the salt, and it's better at surrounding the salt and dislodging it and separating it from the other ions, so it increases the solubility. So yeah, totally. It's totally relatable.
Okay, cool.
Because it's all proportional to temperature, right? So and just like with gases, we saw that too, that the pressure, so that's Gay-Lussac's concept. The pressure increases with an increase in temperature. Why? Because As temperature increases, the gas particles are moving more and they're colliding with the walls of the container more frequently, and pressure goes up. Remember, I had mentioned in the gas laws, think of pressure as proportional to the number of collisions. So if I increase temperature, there's more collisions, there's more pressure. So now we're applying that same concept, right? Just like we did with solubility. As I increase temperature, things get broken, it's easier to dissolve. Well, now we're taking that same concept and we're saying, okay, I'm going to increase the temperature. What does that do to my reaction rate? Well, things are moving faster. They have more energy. What does that mean? A greater likelihood of reaching that activation energy required for a reaction to take place.
Okay,
So
thank
that was
you.
probably, you're welcome. Did
Oh,
that answer it, or?
oh no, yeah, no, yeah, it did, it
Okay.
did. I was just trying to like give myself like a visual or like something relatable to where I can like grasp the concept easier.
Totally. And this next slide, I think, is really going to help a lot of students. I'm hoping, I might be wrong, but I'm hoping this next slide helps everybody. It always helped me because I always took, my freshman year, I was taking chemistry with bio and, calculus and a bunch of other things, but I was taking them together. So hopefully this next slide really rings true for those of you who are taking bio or have taken bio, or I know you've heard of this at least somewhere in your education, K through 12. So one of the things that's a really common discussion are catalysts. Now, most people know that a catalyst speeds up the rate of a reaction, okay? So how is it that a catalyst speeds up the rate of a reaction? So one way to look at it is you have this activation energy, okay? So it's the minimum, right? It's the minimum amount of kinetic energy required to break bonds. Remember, that was one criteria for activation energy. You had enough kinetic energy to break a bond. That was one criteria for what I call the effective collision. Does anyone remember what the other criteria was on top of
Proper
having?
orientation.
Yes, I think that was Jake, and thank you for that. You have to have the right orientation. That was excellent. That's exactly what I was looking for. Thank you, sir. So for activation energy to be reached, you have to have enough kinetic energy to break the bond, and you have to have the right angle. Well, what does a catalyst do? A catalyst lowers this activation energy, right? So how does it lower this activation energy? It provides something to make it a little easier, to lower this energy hump. It provides the correct orientation. So some of you may remember the discussion in your bio classes, or even, I don't know, general science, of enzymes. Enzymes are proteins that speed up reactions. So basically an enzyme is a biological catalyst. And why is that? An enzyme typically has what is referred to as a active site, right? And what happens is the substrate can fit in that active site. And once you form that enzyme substrate, this is a terrible drawing, but we'll just say, once you form that enzyme substrate complex, you can then produce, okay, your two products. All right, so I'm trying to show that this is broken up. You can produce your two products. And the catalyst isn't really involved in the reaction. It's not a reactant. It's just, it has this active site that allows the reactants to fit in at the correct orientation. So by doing that, it speeds up the reaction. And basically your whole body has, I mean, that's one of the main functions of proteins, right? If you look at proteins, there's different classes, structural, immunoglobulins, there's, but enzymes a major class, and that's to speed up reactions, right? Because it would take you forever to digest your food if you didn't have enzymes. Yeah, I mean, you would die before you would get those nutrients. So we rely heavily on biological catalysts. Why? They speed up processes. You see this with hydrogenation of peanut butter. They use metal catalysts to line up the oils and push the hydrogen gas through to break the bonds. So Basically, a catalyst speeds up a reaction by lowering the activation energy. How does it lower the activation energy? It provides one of the two criteria, the correct orientation to activation energy, or what I called an effective collision. And you have to realize the catalyst is not a reactant, so it doesn't really get used up. So what are factors that increase reaction rate? More reactants, more collisions. Higher temperature, more collisions. Adding a catalyst, why does that lower activation energy? Well, Jake said it. It provides the proper orientation. So those are three things that vastly influence how fast reactions occur. Now, in all these cases, I'm kind of showing a positive effect. What if there were less reactants? What would happen there? Would there be more or less collisions?
Less collisions.
So then the reaction would take place slower. What if I, instead of boiling it, what if I put it on ice?
It would move slower.
It would move slower and the reaction rate would decrease.
Yes.
So just don't think one way. I mean, right now I'm covering more going in a positive direction, but you can also have the opposite.